Let's think quickly about where you've been over the last couple or few weeks in thermodynamics class. Let's go back to chapter 8. What was chapter 8 all about? It was about steam power plant cycles and a lot of power, a lot of great practical applications. What kind of substance did we have? Phase change substance. Then you moved on to chapter 9, air standard cycles. Again, all kinds of practical applications. You're learning how to solve problems that are going to prepare you for engineering practice. Substance. All of the substances was basically air that we treat as an ideal gas, and you learned how to solve problems with that substance, air, ideal gas. Now we're moving into chapter 10, and that's going to be vapor, compression, refrigeration cycles. And so the important thing there is, well, now what kind of substance are we going to be working with in chapter 10? The answer is we're back to phase change substances. And so as you do your thinking and thinking about problem solving, thinking about homework solutions in chapter 10, now you're back to looking up properties in the tables, particularly refrigerant tables. So let's get started with a full worked out homework problem from the textbook. I've selected this problem that I think is going to be a good representative and to some extent simple as long as you know the fundamentals. I was going to say as long as you know the secrets, but let's see what this is all about. An ideal vapor compression refrigeration cycle, those are some key words, operates at steady state with refrigerant 134A as the working fluid. Saturated vapor enters the compressor at 2 bar, 200 kPa, and saturated liquid leaves the condenser at 8 bar, 800 kPa. The mass flow rate of refrigerant is 7 kilograms per minute. Okay, great. Determine the 4 things. Compressor power required. Makes sense. The refrigerating capacity in tons, whatever a ton is. Okay. The coefficient of performance. Reasonable question for a refrigeration cycle. And then finally, I've added another part D, the quality at the inlet of the evaporator. Now your head could be spinning and say, I don't understand any of that jargon. Let's start diving down and see what are the fundamentals associated with an ideal vapor compression refrigeration cycle. What do all these things have in common? A refrigerator in your kitchen, a window mount air conditioning unit. You see outside a compressor and condenser contained in this gray louvered device outside your apartment or townhouse or home. And even refrigerate the air conditioning system in your automobile underneath the hood. What they all have in common is they all use the vapor compression refrigeration cycle to keep you or your food and beverages cool. Okay, so back to a basic schematic. What's the objective of a basic refrigeration cycle? Well, the objective is to remove heat from a cold or cool space, function of a refrigerator or air conditioner. And where does that heat go to? It goes to, let's say, the surroundings, okay, or to a warm space. Now, we all know that you can't transfer heat on its own from cold to hot. And so what it costs you to operate this refrigeration cycle is power. So you have to invest power in order to transfer heat from cold to hot. That's the basic idea of chapter 10. Okay, now is where I reminisce about my dad, who was a mechanical engineer, and he did his best to explain to me how a refrigerator worked. And I'm going to have to say that I didn't absorb it. Even after he had explained it to me 3 or 4 times, I just wasn't getting it. And it took me college to understand how a refrigeration cycle worked. But to this day, I can still remember him describing to me these 4 basic elements of a refrigeration cycle. He started with, well, the compressor, okay? And then after the compressor comes the condenser. And then there's a thing called an expansion valve in the back of your refrigerator. And after that expansion valve is the evaporator, and that's where the cooling takes place. And he would repeat that to me, and I wouldn't get it, and I wouldn't get it. All right, well, let's get closer to solving this homework problem, even though I love reminiscing about my dad. To solve our problem, what's in it? What's going on with the compressor? Well, the inlet state is saturated vapor. Okay. The compressor for the ideal refrigeration cycle, the compressor is a reversible and adiabatic, in other words, isentropic process. Next is what the condenser does. It operates at a constant pressure at a high temperature. Hot refrigerant is in the compressor, in the condenser, and due to heat transfer, rejecting heat from the refrigerant, the outlet state becomes saturated liquid, but it's still hot at high pressure. The expansion valve takes that high pressure refrigerant that's hot, okay, expands it, it drops the pressure, okay. The expansion valve is fully insulated. There's no change in kinetic energy, basically. And then we go into the evaporator with our phase change refrigerant. And so the evaporator, it's purely a heat exchanger operating at constant pressure, but it turns out that it's operating at a low temperature, and that's where you get your refrigeration effect. So I'm hoping that helps fill some blanks in. There is nothing wrong with you coming into this class and having no idea what a compressor, a condenser, expansion valve, and evaporator do. So do not feel embarrassed that you don't know how these things work. I'm going to try to fill in some blanks for you. And so here is that schematic diagram of our basic refrigeration cycle. I hope you've got that part. Notice these dots. These dots, we're operating steadily at a certain rate. It's like your refrigerator is running and running and running and removing heat from the cold space. Okay. Now let's look at the equipment. So I plop down those words. I think that doesn't help me visualize what we've got. I hope this is going to help you visualize what we have. Here is our compressor, steady state, steady flow, open system, one inlet and one outlet, operating reversibly and adiabatically. A condenser, it's just a heat exchanger, and it's exchanging heat with the surroundings. So heat is flowing out of the hot refrigerant into the surroundings. Okay, we come around here, steady state, steady flow, one inlet, one outlet. Expansion valve, fully insulated. It's got insulation packed around the valve. Let's see that it's a valve. There's no adiabatic. There's no heat transfer, but also look, the valve's not lifting a weight. There's no shaft attached to this valve, so there's no power associated with this expansion valve either. The pressure drops from high pressure to low pressure, and that's what's we will do some thermodynamics. We'll write the first law to explain how come state 4 is much, much colder than state 3 due to this pressure drop process, irreversible pressure drop process. Finally, the evaporator, a pure constant pressure heat exchanger where the refrigerant is absorbing heat. Heat's flowing in to the refrigerant from the cold space in your refrigerator, for example. Okay, I've tried to show red, high temperature reservoir, blue, cool, low temperature reservoir, and trying to depict we're transferring heat from low to high at the expense of having to run our compressor, having to buy electric power to run our compressor. I hope that makes sense. So I've got to tell you that when I walked into the class in thermo, I did not have a good handle on this stuff. So don't be ashamed if you're not getting this right out of the box. If you want to learn a little bit more about the components of a vapor compression refrigeration cycle, I would try to chase you to my YouTube channel. Go to Example Problems Refrigeration and watch air cond calcs, air conditioner calculations because air conditioner operates on the basic refrigeration cycle. Now to get started, we're moving ahead towards solving our problem, okay? First thing we do after drawing that sketch, we've drawn a sketch of our equipment labeling states 1, 2, 3, 4. The next thing that we must do on your homework solution is draw a temperature entropy diagram, including the vapor dome. Temperature on the Y, entropy on the X. We'll draw the vapor dome. Refresh our memories. Over here, what do we got? Superheated vapor. Under the dome, we have a mixture, saturated vapor, saturated liquid. If we're laying on this line, we've got saturated vapor. If we're laying on this line, we've got saturated liquid. And so, at least in my sketch, I've labeled process 1 to 2. You see it's reversible adiabatic, constant entropy. It's the compressor. Compressor process 1 to 2. Condenser process, it is condensing the refrigerant at constant pressure. Here's a line of constant pressure, condensing it down to saturated liquid. Then we go to the expansion valve, fully insulated valve, not lifting a weight. Expansion valve, process 3 to 4. It's important to show 3 to 4 as a dashed line because the expansion valve is a classic irreversible process. So you don't show it as a smooth line, you show it as a dashed line. That indicates to other engineers you've got an irreversible process. Process 4 to 1, that's the evaporator process where heat is being transferred into the refrigerant from the cold space. Okay, 4 to 1, that's the evaporator process. Steady state, steady flow, one inlet, one outlet. Oh, and then remember that I've added a little extra credit for a reason. What will the quality at state 4 be? Find X4. So I hope you remember now. Let's see. Saturated vapor, that's like H sub G. Let's see. Saturated liquid, that's like H sub F. So when you're between H sub G and H sub F, you're a saturated mixture. So I'm going to show you how to find X4, the quality at state 4. Absolute must to draw this TS diagram. Okay, what is wanted in the problem statement? Well, m dot is given. That's a gift for this problem, 7 kilograms per minute. We're going to watch out for our units. Want the compressor power? Well, let's see. That's W dot of the compressor. We expect it to be a negative number. And what we're going to do when we go through the solution, we're going to deal with little w of the compressor and multiply it by m dot to get W dot. The refrigeration capacity in tons, whatever a ton is. Now, just to speed up the process, I've pulled out a screenshot of our conversion factors from your one-page conversion factor book, and I see that 1 ton of refrigeration equals 211 kilojoules per minute. So we're just going to accept that as a conversion factor for units. Now, when I went through, and my dad explained to me that a ton of cooling also equals 12,000 BTUs per hour in the English system of units. And so this, for most engineers, this is a very familiar conversion that we won't use in this problem. We're going to use this other one that I have not committed to memory. Okay, refrigeration capacity, how are we going to get that? Well, we're looking for Q dot, capital Q dot. We're going to calculate QL. We're going to show that we're going to apply the first law to show that QL is H1 minus H4. You don't want to blindly simply accept J's solution as a formula. That would be a bad move. Okay, we're going to go through the fundamentals, okay, to get the refrigeration capacity. Coefficient of performance, energy sought over the energy that costs. And I hope that this video has convinced you that the energy sought is Q dot L, the refrigeration capacity, divided by W dot, the power required by the compressor, basically a positive number. That's part A, the compressor power required. Okay, and so, and let's see, what else do we have? The evaporator inlet quality, we're going to calculate that, X4, and we're going to use our TS diagram to visualize how to get started with that. Okay, let's go through and plan our work before we put pencil to paper. Let's analyze the compressor. Well, here is what a refrigerator or heat pump air conditioning system compressor looks like. So you can see there's an electric motor up down below. That's the electric motor driving a compressor, a rotating scroll compressor. Okay. Here's what the compressor looks like on our equipment diagram. Inlet state 1, outlet state 2. Let's see. We're given in the problem that it's saturated vapor. So what we'll do first is look up, we'll tabulate S1 and H1 because we're looking ahead. We know we need S1 to get state 2 to find out what state 2 is. We're going to write down H1 because we know we're in thermo class. We know we're going to write the first law for the compressor. Steady state, steady flow, one inlet, one outlet. All right. So let's see. If we've written down S1, then we know what S2 is. S1. We also know P2 is 8 bar. So you've got two independent properties. If you've got two independent properties, it's sort of child's play to find H2. I'm going to show you how to do that. And then we'll use the first law to find W of the compressor. And since it is adiabatic compressor and reversible, we're going to be able to solve flat out for W compressor. Little W compressor, W dot over M dot is simply going to be H2 minus H1. Then we get to the condenser and we do some thinking and say, okay, what do I need to do with this condenser? And we're going to skip the condenser. Why? For this problem assignment, let's see, part A, we're asked for the compressor power. Do you see it has nothing to do with the condenser? Part B, the refrigeration capacity. Well, that's down in the evaporator. Doesn't have anything to do with the condenser. Part C, the coefficient of performance. Well, that's just going to be part B divided by part A. Part D, the evaporator inlet quality. We're interested in X4. So we're interested in sort of the evaporator process. So none of our work involves the condenser. Oh, what does the condenser look like? I've shown a little screenshot of this would be a home air conditioning condenser that sits outside your home, and the condenser coils behind these louvers. That's what's rejecting heat from the hot refrigerant out to your surroundings. So this is a picture of a residential air conditioning condenser. Also, the compressor is also inside this unit, but we won't worry about that right now. We are going to move to the expansion valve. So we're going to skip the condenser, move to the expansion valve. Let's see. We will write the first law for the expansion valve because do you see that? Well, in the problem statement, it said, look, H3 is saturated, or state 3 is saturated liquid. That's going to be easy. We know the pressure at state 3. We will look up H3 is simply going to be H sub F at P3 equals P2. That's easy. We'll write the first law for the expansion valve. Well, let's look at this expansion valve. Here's a photograph of a real refrigerant expansion valve. Here's a cutaway view of this refrigerant expansion valve. And so notice it, here's the inlet state. That would be state 3. Outlet state, that would be state 4. So notice how in the cutaway, basically the flow is going through a tiny little orifice compared to the diameter of the inlet and the larger outlet. Okay. And so the high pressure to low pressure, 3 to 4. This is a classic throttling valve or expansion valve. The throttling valve, if we write the first law, then is this valve, do you see a weight being lifted? No. Do you see a shaft coming into or leaving the valve? No. So there is no work out, no W dot over M dot. We're going to say that this valve is fully insulated, which is a good model. And so the first law, Q little q in minus little w out, both are 0, equals H4 minus H3. As long as there's no change in kinetic energy, and it said that in the problem statement. So we're going to demonstrate that H4 equals H3. Don't fall into the trap of saying this is a formula. I'm going to blindly write down H4 equals H3 and move ahead. Do you see that H4 equals H3 is an expression of the first law of thermodynamics for this expansion valve for steady state, steady flow, open system, one inlet, one outlet? Okay. Really want to encourage you to develop that mindset instead of the what's the formula mindset. Okay, what do we do next? We're still working on solving this, but we're planning our work. We will analyze the evaporator. Let's see, we just showed that H4 is now numerically known. H1, we've already looked that up. That's saturated vapor that we've already written down a number for. So do you see that little QL, Q dot L over M dot, is simply going to be equal to H4 minus H1. Again, my same lecture about first law. This is not a formula. QL equals H1 minus H4. Not a formula. Statement of the first law. Okay. Let's see, QL. If you numerically think about these numbers, you're going to see that QL is going to be positive. Heat is being added to the refrigerant. Now, find X4. That's part D that I've assigned. I've assigned that because this is a common test question that often doesn't appear in homeworks. So I want you to be heads up. Get good at this. This can save your bacon when you're taking a test. Okay. How will we define X4? Well, I've tried to draw a partial screenshot of our TS diagram. So here's state 4 coming out of the expansion valve, saturated mixture. I'm going to write down H sub G and H sub F at P4, which is a known value. I'll look those two up. And then I'm going to simply remember my definition of quality. It's a ratio. It's this distance in terms of enthalpy divided by this distance. It's a ratio. That's what the quality is all about. It's the mass of the saturated vapor divided by the total mass of the mixture. It's that ratio. And there it is. H4 minus HF divided by Hg minus HF. Simple as that. And we're done. Okay. What does the evaporator look like? Here's a photograph of an evaporator for a home air conditioning system that's sort of a whole house air conditioning system. Hot or warm return air that's coming back from your house, from your rooms, is coming in low, and it's flowing across these coils full of refrigerant that is flowing 4-to-1. Okay, so the refrigerant is flowing in these coils, and then the cooler air is coming out of the top and headed towards the supply air that keeps you nice and cool in your house. So that's what a home HVAC whole house air conditioner evaporator looks like. Okay, I've drug you through, we've planned our work, and that's usually a pretty good idea to do. So now let's go through the numerical solution. We need to get H1 first. So we're going to start at state 1 of the compressor, inlet of the compressor. Here is our pressure in bars. So we're simply going to write down, let's see, we're going to write down H sub G. H1 is 241.3. S1 is 0.9253. And planning ahead for that X4 business, while we're here, we will write down H sub F 36.84, and we'll set that aside. 36.84 kilojoules per kilogram. Let's see, Hg, kilojoules per kilogram, and S sub G, or S1, kilojoules per kilogram degree K. We're going to write those down. Okay, what's the next thing we're going to do? We're going to analyze the compressor to determine state 2. All right, so we have observed, we wrote down S1. So S2 equals S1. We're going to go to the superheated tables. We saw on our TS diagram that state 2 is superheated vapor. So we go to our superheated vapor table for refrigerant 134A. Let's see, it's 0.9283. Uh-oh, it's in between these two numbers. So H is going to be between these two numbers. And the temperature, is going to be between the number sat and 40. What's the number sat? Oh, here it is. The saturation temperature is 31.33. So this number right here is 31.33. You're not required to find it, but we're going to find it in our solution. What you're required to find is H2. You need H2. And so here it is, okay? We wrote down H1 and S1. We observed that S2 equals S1. That's our isentropic compressor. We set up an interpolation table. So here were the two straddling S values. Here is our S value, S2. And then we wrote down the temperature entries, sat, 31.33, 40. Get a little extra credit for that. But what we really need is H. So we wrote down our straddling H values. You do our linear interpolation to get the T2 is 36.59, and H2, what we really need, is 269.9 kilojoules per kilogram. Okay, great. Why did we go through to get that? Because we looked ahead and we're going to use the first law, steady state, steady flow. Sorry about that. Yikes, sorry for this confusion. I hit my mouse too quickly. First law for the adiabatic compressor, Q in, 0, minus W out equals H2 minus H1. Solving flat out for W of the compressor, W dot over M dot is negative, good, 28.62 kilojoules per kilogram. We have found, and so let's see, we can immediately write down the given M dot, 7 kilograms per minute. So we can immediately calculate the W dot, I think that's part A, right? W dot for the, let's look at our units. Kilojoules per kilogram times kilograms per minute is going to give us kilojoules per minute. That's not a kilowatt, is it? A kilowatt is a kilojoule per second. So I've got to divide kilojoules per minute by 60. That's a conversion I use in my head. So you should be using it too, right? You know that there's 60 seconds in a minute. So I'm going to divide 200 by 60 to get negative 3.34 kilojoules per second. And that is a kilowatt. And so in my solution, I'm going to write down, I'm going to take the negative of that and write out in words, the compressor power required is 3.34 kilowatts. And I would circle that as my answer with words. Okay, next thing we're going to do is analyze. So we're moving on, but we're making great progress. We're going to analyze the expansion valve. We skip over the condenser. Expansion valve. Let's see, we're given saturated liquid at state 3. So we'll go to our pressure table. That P3 is given, 8 bar, and it's saturated liquid. So I'm simply going to write down that H3 equals 93.42 kilojoules per kilogram. We went through the planning stage to see that H4 equals H3 by way of the first law for the insulated expansion valve. It's not lifting a weight, no shaft output. So H4 equals H3. Numerically, we've got H4 now, 93.42. Next thing, analyze the evaporator, and we're done. Okay, let's see. H4, we just wrote down 93.42. H1, we already have it, 241.3. So first law for the evaporator, QL, there's no work associated with the evaporator, is simply going to be H1 minus H4. Yes, H1, the outlet, minus H4, the inlet. Q, little q, minus little w, that's 0, equals H out, H1, minus Hn, H4. So QL is positive 147.9 kilojoules per kilogram. M dot, given from above. So Q dot L is 1,035 kilojoules per minute. And now what pays off is that work I did to fish out the conversion factor of kilojoules per minute to 1 ton of cooling, 211 kilojoules per minute in 1 ton of cooling. I'm going to check my units to see that I've got to divide by 211. So I've got Q dot L is 4.91 tons. That's a significant size of a refrigeration cycle. So this is probably some type of commercial or industrial refrigerator, because typically whole houses might require a 3-ton air conditioning system to cool an entire house. And so 5 tons of cooling for a refrigeration cycle, that's a pretty hefty size refrigerator. All right. Oh, our extra credit, the quality at state 4. Let's see. How do I get X4? Well, I have H4. All I have to do is look up H sub G and H sub F. I wish I'd have labeled that here on my sketch, H sub G and H sub F, okay? And I wrote both of them down, and here's 36.84 that I had way back that I saved off to the side, okay? H4, just got to look at that from above, and we're going to apply the definition of quality. It's going to be this distance, H4 minus HF, divided by this distance, Hg minus Hf. So the quality is 27.7%, 0.277, 27.7%. So I've got some remarks. We finished the problem. Oh, no, coefficient of performance. We've still got to do that, don't we? Easy. Now that we've been through all the numerics of the problem, it's the energy sought, little w of the compressor, divided by the energy sought, QL, the evaporator heat transfer, energy sought, energy that costs, W of the compressor, W dot over M dot, required, power required, work required, okay? And so you do see that I've wiped out the minus sign here, work, but I'm, in my words, I'm saying W compressor required, and so the coefficient of performance is 147.8 divided by 28.6, or 5.17 is the coefficient of performance for this ideal refrigeration cycle. Let's put it all together and sort of recap a little bit. The compressor power, the answer given was 3.34 kilowatts. Woo, we got it. Okay. The refrigeration capacity, well, in our solution, we found some large number of Q dot, okay, but we had to apply our conversion factor to get 4.91, agrees with the given answer. The coefficient of performance, energy sought over energy that costs, we've got 5.17, yay, okay, and the quality at the inlet of the evaporator. So a point that I didn't make strongly enough, and I thought I had put some notes in for Part D. Why am I forcing you to go through Part D? Part D is a classic quiz or test question. And so as you're working through these refrigeration problems, this problem is very similar to an example problem given in your textbook. I encourage you to not go through the what's the formula mindset, but go through the fundamentals for analyzing each component on its own, because I think in the text, they don't go through this exercise with their sort of derivation of their formulas based on the first law and second law. They don't go and show you how to calculate the quality at state 4. This is a classic quiz and test question that tests students' performance on their understanding of what they got, that goes beyond applying some formulas that you don't really fully understand what the formula is all about. So here's a picture of you and your head, and my suggestion is this is your best formula sheet. Your head is far better formula sheet than a sheet with a bunch of specialized formulas on it. So that's it. That is a demonstration of the ideal vapor compression refrigeration cycle. I hope you've gotten something out of it. I hope it improves your understanding of what's behind these refrigeration cycles. And one last memory of my dad. So my dad was class of 1941, mechanical engineering from Virginia Tech. In 1941, refrigeration cycles were a relatively new technology. It's kind of like high tech. And so that was why he was so interested in refrigeration cycles. He did his best to describe to me how they worked, and by golly, I was not getting it. So thank goodness I also became a student in mechanical engineering so that I could get it. Hope that helps you. Hope that helps you understand what's behind the components of refrigeration cycles, how they fit together, and how they work.